All right, here's a review for what's called Exam 4. This is an exam that I did not make up, but I'm doing for someone else. This is Math 3A. The first one, this car is traveling down a straight road at 100 feet per second. Notice that this is in feet and feet and feet, so this you don't need at all. Just get rid of it right now. Okay, so this can be the road. Make my fancy little car. There you go. The car is traveling down the road. There's going to be a speed detector, so let's just say that that's up here on a bridge or a pole or something like that. It's 20 feet above the road. Now when you start labeling these pictures, if things change, you cannot put a number. So for example, down here, as the car goes from here to eventually right here underneath this pole, this distance is going to be changing. So I can't use a number on this. I have to use a variable. I'll call it x. It says that the speed detector is 20 feet above the road. So it doesn't say that the speed detector is moving. It's always going to be 20 feet above the road. So for this side, you're allowed to go ahead and put 20 feet. That's not going to change. Next, how fast is the distance between the car and the speed detector? So that's this distance right here. The direct line of sight distance between these two, which I'm going to call S. In physics, S is often used for distance for some reason, so I'm going to go ahead and use that. Well, notice that I've got a right triangle, so right here it says write a function, and we can do that using the Pythagorean theorem. So it's going to be S squared equals 20 squared plus x squared. All right, that's what's called the main equation. Later on, I'm going to be taking the derivative of that, but I want to finish reading the problem, and I'm going to write down that extra information over here on the side. One thing is, the car is traveling at 100 feet per second. So when it's talking about a speed, it's telling you the first derivative. So the derivative of x, in other words, the difference of x, or how does x change, with respect to time, seconds is time, so it's going to be with respect to time, and it says that the car is traveling, or its velocity is 100 feet per second. And you can either use the units here or not. Right now I'm not, because everything is in feet. I've already checked that, so I'm not going to get tricked later on that one thing is in feet and another thing's in inches or something like that. Everything's in feet, so I can just leave the labels off for right now. Okay, the next thing is how fast is the distance. So when it says how fast, it's asking you for a derivative. The distance between the cars, so that's saying this distance right here. How fast is this distance changing? So as the car goes from here to say right here, of course x got shorter. Well, s would go from here to here, so s is getting smaller also. So we would have ds dt is what? That's what we're supposed to find. Next up, when the car is 200 feet from the spot. So they're saying find the derivative when x is equal to 200 feet. All right. Now, since we have the Pythagorean theorem, we can go ahead and substitute 200 in. I'm not going to do it over here because this space over here is for when I do the calculus and actually take the derivative. Over here, this is my numerical information. It's sort of like this is going to be my algebra over here. This is going to be my calculus over here. So with the algebra, what I can do is substitute 200 into this equation over here for x, and it would say s squared is equal to 20 squared plus 200 squared. So that is 40,000, and that is 400. So s squared equals 40,400. And then when you take the square root, you should say plus or minus the square root of 40,400. And with the plus or minus, well, distance is not usually measured as a negative. So I don't know that I would really use this negative, but I'm going to leave it on here because, as I'll explain in a second, we actually are going to end up using the negative. Okay, so you could get the decimal form of this if you want. I'm just going to leave it as the square root of 40,400. Next, we need to go over here, and according to this, we're supposed to find the derivative. So here I'm going to use implicit differentiation. Take the derivative of s squared is 2s. And then the chain rule says you need to take the derivative of the inside. So the inside is the letter s. So I've taken the derivative of the outside, the 2 goes down in front, subtract 1 from the exponent. Now take the derivative of the s. That's going to be the derivative of s with respect to t. On the right-hand side, this is a constant, so the derivative is 0. The derivative here is going to be just like I did with s. It's going to be 2x, and then you have to take the derivative of x, so dx dt. Now that we've done this calculus over here, we should be able to use this algebra over here and plug in the information that's given. So for example, this is known to be 100. This is known to be 200. S we found to be the square root of 40,400. Then all we have to do is solve for ds dt. Right now you have the choice of plug in the numbers and then solve for this, or solve for this and then plug in the numbers. I'm going to go ahead and solve for this and then plug in the numbers. So I need to divide by 2s, so divide both sides by 2s. It's going to leave ds dt on the left side. When you divide the 2's, they're going to cancel, so this side is going to say take x and dx dt, divide both sides by s. So when we substitute in the numbers, ds dt is, let's see, x is 200, dx dt is 100, and for the denominator, s is this. And as I said, technically, when you take the square root of both sides, you're supposed to put plus or minus. Okay, now you could go ahead and type this into a calculator and get a decimal answer, but I'm not going to do that right now. One last thing that I want to talk about is this plus or minus. Well, when you say ds dt, that means how fast is something going. If something's getting bigger, we usually say that the derivative is positive. If something's getting smaller, then we say the derivative is negative. So derivative in this case means a velocity, and you may think, well, how can there be negative velocity? Well, that just means it's going backwards or it's shrinking. So as the car goes from here to here, the s is going to get smaller. So since it's getting smaller, I would say ds dt equals the negative, and then just get whatever decimal this turns out to be when you type this in the calculator. Okay, next up. This question is asking a lot of parts at the same time. So it's saying this is the distance. So it's saying s equals distance. Can you see that? Here you go. And the first derivative is velocity. The second derivative is acceleration. So if you were talking about a car, S would be how far did you drive? 20 miles. S prime would be how fast did you drive? 60 miles an hour. And the second derivative would be your acceleration. So as you went from 40 miles an hour to 60 miles an hour, you accelerated by 20 miles an hour. So distance, velocity, acceleration. It's used throughout calculus over and over again, so you definitely need to know that. Okay, next it's saying, when is the particle moving to the left? So this is the thing I was talking about right up here. If something is getting smaller or going backwards, we say the derivative is negative. So this part right here is saying, when is the derivative negative? And as I said, acceleration means second derivative. So this part is saying, when is the second derivative positive? So once we've interpreted that calculus, that this is saying, when is the first derivative negative, because of the word left? When is the acceleration positive? So when is the second derivative positive? Then we need to take the first derivative, find out when is that negative. So I'm going to call that part A. The first derivative, and you could call it ds dt, or you could call it s prime for short. Just like over here, I could have called this dx dt, or I could have called it x prime for short. Both notations are used, and sometimes I interchange. Sometimes I'll use the dx dt, sometimes I'll use x prime. So I'm going to interchange. Over here, I could use ds dt, but I'm going to use the shorthand s prime. So take the derivative, the 3 goes down in front and multiplies. It's going to cancel the 1/3, subtract 1 from the exponent. Over here, take the derivative. It's going to be negative 10t. The derivative here is just going to be the number 21. And the derivative of 8 is 0. Since we need to know where this thing is negative, that's what this part's saying, where is the derivative negative, then what I'll do is set it equal to 0, and this one, thank goodness, can be factored into t minus 7 and t plus 3. So this one, when you set it equal to 0, that would say, hey, wait a second, back up, back up. This should say t minus 3, because if we're going to get a positive 21, we need negative 7 times negative 3. One of the rare times I need to use an eraser. There we go. Okay, so our two solutions are that t equals 7. In other words, after 7 seconds, the derivative equals 0. That means that it stopped. Also, at t equals 3 seconds, this thing stopped. So basically, if you watch my pencil, it would be like this. The thing went, after 3 seconds it stops, and then it goes back. And it goes back and back and back and back and back. And then after 7 seconds, it stops. And then it goes this way. So this thing is going back and forth on a straight line. So it's not just going one direction, but according to this, it's going to go back and forth. Okay, so we need to know when is this thing moving to the left and when is this thing moving to the right. So when is the first derivative negative? There's a few ways you can do that. The old-fashioned way, back when I was a student, we had to go like this because we didn't have graphing calculators. You put a timeline. Here's time equals 0. Here's 3 seconds. Here's 7 seconds. And then what you do is, in this interval, you want to know, is it going to the right or to the left? So you pick any number in here. I'm going to pick 1. and then you test t equals 1. So you go up to the derivative, substitute in a 1, and what we're looking for is this a positive or a negative? So positive means it's going to the right, and negative means it's going to the left. Well, this is going to be 1 minus 9. Oh, excuse me, I'm saying the answer instead of the question. 1 minus 10 is negative 9. And then negative 9 with 21, well, that's a positive. So that means all in here, it's positive, which means that it's going to the right. Then in this interval, you would pick a number like 5 or something like that. And then this would be 25 minus 50, so that's negative 25. Negative 25 and positive 21, that's negative whatever. I don't really care what the number is, it's negative. So that means that all in here, it's going to be negative. Then pick a number over here like 8. You know what, I'm going to pick 10. That would be easier. I'm going to pick 10. So pick any number to the right of 7, like a 10. Plug in a 10. This would be 10 squared is 100. This would be 10 times 10, so that's 100. When you subtract these two, it's 0. It leaves you a positive 21, so it's positive. So that means this thing was going to the right, then going to the left, then going to the right. Okay, so that is about this question. When is it moving to the left? So it's this middle interval when it's going to the left. So far, we've taken care of that word right there, the word left. That's what all this work was for. So it's going to the left when time is between 3 and 7. Now we need to know this part, positive acceleration. So acceleration is second derivative. So take the derivative of the derivative. The derivative of this derivative is going to be 2t minus 10. So you start by setting it equal to 0. Take the 10 over, it will be a positive 10, then divide both sides by 2, and it says t equals 5. So if you put a time interval, and since time isn't negative, we can't go backwards in time, although there's many times I wish I could. We can't, so we started at 0. So time starts at 0, then here's 5 seconds later. And then you do the same type of thing. You pick a number in between, so I'm going to pick easy 1. You test t equals 1. And then that needs to be substituted into the second derivative. So the second derivative, when I test the number 1, is going to be 2 times 1 minus 10. So that's going to be 2 minus 10 is negative 8. The negative is what's important. So all in here, it's negative. Then at 5, it's going to change. So you pick a number over here like 6. The second derivative at 6 is going to be 2 times 6 minus 10, which will be 12 minus 10 is a positive 2. The 2, I don't really care about, but it's a positive 2. So all over here, it's positive. So this interval tells you it's negative acceleration, which in plain English we call deceleration or slowing down. So here it's slowing down, here it's speeding up. So it's going to the right, and then to the left, and then to the right. And on the interval from 0 to 5, it's slowing down. Okay, finally to This one. This one is saying positive acceleration, so that's from 5 on. But this one is saying to the left. So we have to put the two answers together. This says it has to be between 3 and 7 seconds. This one, this one, positive acceleration, says it has to be bigger than 5. Well, if it has to be both bigger than 5 and between 3 and 7, that means it has to be between 5 and 7. So the final answer is left and positive acceleration. That's when it's between 5 and 7. Ta-da! Quick note, don't put any equals on this because this says positive. Well, if you were to put an equals on this, that would mean that it could equal 5. But look, if you put a 5 in there, exactly 5, this would be 2 times 5 is 10, and then 10 minus 10 is 0. And 0 is not a positive. So I don't put an equals. Likewise, I don't put an equals on this. It's just between 5 and 7. Okay, on to the next one. When is it speeding up? When is it slowing down? So speeding up would mean accelerating. So just like in your car, when you speed up, so you're not just constantly going 50 miles an hour, but you're speeding up. You're going 50, 60, 70. So this means acceleration is positive. Slowing down means acceleration is negative. So all of this was a lot of work, but the good thing is that then answers this question. Speeding up, that means positive acceleration, so that's right here. So speed up, that's right here, positive acceleration. So that means when t is bigger than 5. And then for slow down, that would be between 0 and 5 seconds. So this interval is slowing down, this interval is speeding up. And that is number 2, just barely fitted into the space provided. Okay, next for number 3. Let me get my page. Here we go. So this question also asks a lot of information. There we go. And it's emphasized that you're supposed to do this without a calculator. Well, one thing I noticed without a calculator is that you can't take natural log of a negative. So that means that this part of the graph is out. That's a waste of space. So even 0, I can't have 0 because of this, and technically this also, but you can't divide by 0. So if I'm going to do this without a calculator, I'm going to make a little table of values. Then 0 would be undefined, so I might as well go like 1, 2, 3. And if I substitute in a 1, now it says without a calculator at all. Well, okay. When I substitute in a 1, this would be 1. Natural log of 1 is 0. This would be 3 divided by 1. So this would be 0, this would be 3, and this would be 1. So it's 1 plus 3. Without a calculator, that's usually 4. So it would be 1, and then 1, 2, 3, 4. It would be right here. I also know that without a calculator, this and this both have asymptotes. This you cannot divide by 0. So what happens if instead of putting 0, you put something really close to 0, like a half? So I'm going to need to put that right here. Well, let's see. If it was a half, it would be a half plus 2 natural log of a half plus 3 divided by a half. So this would be 1/2. This would be 2 times 0.693. Because we're not supposed to use a calculator, of course we have memorized that natural log of a half is 0.693. I think the teacher meant on this one to say without a graphing calculator, because I would assume you could use a calculator to figure this out anyway. Then 3 divided by a half, you have to invert and multiply, it turns into a 6. So this is like almost 1.4, this is 0.5, so that makes 1.9. 6 plus 1.96, it's 7.9 or something like that. So 7.9 would be, so I go to a half and about 7.9, that would be up here somewhere. So the graph would be going like this so far. Next, substitute in a 2. So what happens when it's a 2? So we would have 2 plus 2 natural log of 2 plus 3 divided by 2. Okay, I'm using a calculator. 2 plus 2 natural log of 2, and then plus 3 divided by 2 of 4.886. So for 2, you go up to 4.886, and then substitute a 3 and maybe a 4, but what you'll find is the graph looks like this. I don't want to spend all day graphing this by hand, but the graph looks approximately like that. So local maximums, it looks like it doesn't have any because this is going to keep going up forever, and this side's going to keep going up forever. So I'm pretty sure the answer to this is none, although right now I'm going to write it sort of lightly in case I have to change it. Local minimum, that looks like this point down here was the lowest point, so that was at 1, 4. So I think it's at 1, 4. Where is it increasing? So that would be when it's going from the bottom up. So that would be from here, when x equals 1 to x equals 2, it's going up. X equals 3, it's going up. So that means when x is bigger than 1. Another way to write that is from 1 to infinity in interval notation. The directions didn't specify which way I have to write it. And for decreasing, that's this part. It's going down, going down. So that's only when it's in here. Between 0 and 1, it's going down. So decreasing, so you could say it's between 0 and 1, or you could write it in interval notation from 0 to 1. But I haven't done any calculus yet. Well, all of this, the first 4 right there, that's really done with the first derivative. And then points of inflection and concavity. So concavity means like when it's shaped like this, that's concave down. When it's shaped like this, it's concave up. This is done with the second derivative. Okay, so now we're going to get to the calculus. So we need the first derivative. The derivative of x is 1. The next one, the derivative of natural log of x is 1 over x. And then this one, you could rewrite it as 3 and then x to the minus 1. Take the derivative of that, it's going to be negative 3 x to the minus 2. And then rewrite that without a negative exponent, and it's going to become negative 3 over x squared. So there's our first derivative. Note on this, x cannot equal 0. All right, now what we need to do is find out where the derivative equals 0, and that should be right here. When it hit the bottom, the tangent line would be horizontal, and the derivative equals 0. So we should, when we set this equal to 0 and solve for x, we should get the answer x equals 1, if our picture was correct. So set it equal to 0. And then solve for x. What I'm going to do is multiply both sides by x squared to get rid of the fractions. In general, when you're doing algebra, you have to be careful to not multiply both sides by a variable, because it's possible that x equals 0, but luckily for us, we already noted that x cannot equal 0, so that means that this algebra is legal. Over here, this, of course, will be 0. 0 times x squared. When you distribute, this is going to be x squared plus 2x minus 3. And then, thankfully, the teacher made this up so that it's easy enough that you can factor. So it's going to be x, plus 3, and x minus 1. So let me double check. This would be negative 3. This is 3x minus 1x is 2x. Okay, so this would be x equals negative 3, which actually I can throw that answer away because in the original problem, natural log, you can't have negative 3 for x. That's not in the domain. So even though the algebra found us this answer, we can't use that one. And then x equals 1. Just like I said, it turns out that our graph was correct. Right here, the derivative equals 0, which is where x equals 1. So that means that my answers that have 1, this one is correct, so I can go ahead and leave that. This one is correct, I can leave that. The local minimum, 1, 4. Now, on the picture, I found out that there's no local maximum, but this was a pretty rough sketch. I didn't even use a graphing calculator. But notice that we only found that the derivative equals 0 when x equals 1, negative 3. The negative we have to throw out. So the only place where the derivative equals 0 is x equals 1. So what that tells me about the graph is, one thing it says is this is correct, which means this is correct, 1, 4. But what it also verifies is that the graph doesn't go like this. Because if it did, right here, at x equals 7 or something like that, the derivative would have to equal 0 if it's got a maximum. But we did not find the derivative equals 0 any place other than 1. That means local maximum, there's none. This part was correct. So it just keeps going up forever. All right, what else is there? Intervals of concavity. Well, by looking at the picture, all of this looks concave up. But you have to be careful because there are times when a graph will look like this. And what will happen is, I'm not saying it happened on this one, but it can happen, that this is concave up. And because our graphs are not very accurate, we can't really see that this part is concave down. So it could be that this is just ever so slightly curved like this, concave down. So what we have to do is, we have to find out, is there a point like this, which is called a point of inflection? And that comes from if the second derivative equals 0. Question mark. Does the second derivative equal 0? Does it go from concave up to concave down? That would be the inflection point, if there is one. So for that, we're going to need the second derivative. So go back over to here where we have the first derivative and take the derivative of this. So the derivative of this, no, we need second derivative. Let me label my work. The derivative of 1 is 0. The derivative of 1 over x, well, that's just like we did right here, without the 3, of course, but you take the derivative, it would give you a negative in front, then give you x to the negative 2. So that changes to negative 1 over x squared. That's a derivative that we use so much, I don't even go through that algebra part I just showed up here. Instead, I just remember derivative of 1 over x is negative 1 over x squared. So it's going to leave the 2 there, and then, the positive 2 there, and then it's going to be negative 1 over x squared. Likewise, you could take this one, rewrite it as a negative 3 and then x to the negative 2. The derivative of this is going to be 6 and then x to the negative 3. So bring the negative 2 down, it becomes a positive 6, subtract 1, this becomes a negative 3. So plus 6, and then instead of writing x to the negative 3, I'm going to write x to the 3 in the denominator. And again, we need to set this equal to 0. Again, notice that x equals 0 makes it undefined. And if you look at the graph itself is undefined at x equals 0. So right here we should say note x cannot equal 0, but we've already said it right there, so I don't need to repeat myself again and again. Let's see, I can do like last time and get rid of the fractions, multiply by x cubed on both sides. So this is going to be 0 equals, and then distribute the x cubed, so this is going to be negative 2x plus 6. So when you solve this, it's going to tell you x equals 3. Well, so that means that at x equals 3, it changes concavity. So if you go back to the graph, my first graph wasn't completely accurate. It is a situation like this, that at x equals 3, right here, it's changing from being concave up to concave down. And if you look on a graphing calculator, you could have something that looks like this. You could have something that looks like this, where you think, well, that's just a straight line. But if you were to zoom in more, you would see that it's actually shaped like this, which is concave down. So you really need to trust the calculus and the math more than the graph or the graphing calculator. Okay, back to x equals 3. So you could do the same thing that I did last time and say, here's a number line, here's 0, here's 3, and then pick a number in between, substitute it into the second derivative and see if you get a positive or a negative. Well, if you test, let's say a 1, just pick something easy between 0 and 3, and you test x equals 1, the second derivative is going to be 0, and then this would be negative 1 over 1, so that makes the 2 negative, and then put a 1 right here, so that's going to be plus 6. So this is a positive 4, so it's positive. So this whole interval would be positive. Then you pick something over here, let's say like a 5, and you test x equals 5. And we want to know, is the second derivative positive or negative? So it's going to be second derivative, when you substitute a 5, will be, so put a 5 right here, is going to be negative 1/25 and then times the 2. This one, if you put a 5, it's going to be 5 cubed is 125. So plus 6 over 125. Sorry, my screensaver just went on. It startled me. So this is supposed to say 125. So when you put this together, it equals whatever, but it's going to be a negative. Type it in the calculator and see. This will be some negative small decimal. So that means this part is negative. So this is where it's concave up, and this is where it's concave down. And at x equals 3 is where it changes. Okay, let's see if we can finish this up. Intervals of concavity. So this part is concave up. So that's when x is between 0 and 3. So concave up between 0 and 3. And then concave down from 3 on. Last, the point of inflection. So that's this point right here when x equals 3. So we need to go back to the original function. We need to finish this little table right here. We never plugged in when x equals 3 to the original. So go back to, here's the original. Substitute a 3. So it's going to be 3 plus 2 times the natural log of 3 plus 3 divided by, and x is at 3. 6.197. And last, that's the point of inflection. My paper is getting a little bit messy right here, but it's 3, 6.197. There's the point of inflection. All right, that was number 3, and then on to the last page. So determine if it has horizontal asymptote. So the general idea is the function does whatever, but after a while, does it level off? And it could go this way too. Does it level off? This part isn't so important. So what it's really asking is, if you take the limit of the function as x goes to infinity, does that become a constant number? So what's the answer to this limit question? So if you have infinity, this would be infinity squared, which is still infinity. This would be infinity and this would be infinity. So you'd have infinity on the top and you'd have infinity on the bottom. So this is a great place to use L'Hopital's rule. L'Hopital's rule says the answer is going to be the same if you take the derivative of the numerator and you take the derivative of the denominator. Basically, it's saying these two things, the numerator is going to infinity, the denominator is going to infinity. But by taking the derivative, you're finding out how fast they're going. So how fast is this one going to infinity? How fast is this one going to infinity? So I just take the derivative of the numerator, and what I ask my students to do is either write out the word L'Hopital's rule so that I can follow their work, or you put a little thing like this, an abbreviation for L'Hopital's, and that just means you take the derivative on the top, that's 2x. Take the derivative on the bottom is going to be 1 plus e to the x. And then you repeat the process. If x is going to infinity, this is going to be infinity, this is going to be infinity, so the answer is infinity divided by infinity. And you might think, well, if you have the same thing divided by itself, the answer is 1. But that's not true because it depends on how fast is this going to infinity and how fast is this going to infinity. So we get to do L'Hopital's rule again. Which is easy to do. You take the derivative of the top is 2. The derivative of the bottom is e to the x. So then we get 2 divided by infinity. So that's saying take 2 and divide it into an infinite number of parts. And if you do that, how big is each part? 2 divided by something really big is really small. In fact, it's so small that it's 0. So the answer is yes, it has a horizontal asymptote. And it's going to be y equals 0. So that means, that's my answer, that means that this graph, the general idea was right, but it's more like this. It does whatever in the middle, and then it eventually goes down to 0. And then you could use the graphing calculator to check that. Number 5, there's a rectangular box. Now you get to see my fancy 3D drawing. There's the face of the box. There's the back of the box. The top, whoops, the top, the side, and then check this out. I put a dotted line for 3D perspective. It's an open box, so it has no top. It's twice as long, so this is going to be how long it is. It's twice as long as it is wide. So whatever this width is, which I don't know, so I'll call it x, this is twice as much, 2x. And then it says nothing about the height, so I'm just going to say h for height. Next, the question is about volume. So volume is equal to the length times the width times the height. So volume, in this case, is going to be multiplied these three sides. X times 2x times h. Or in other words, volume is equal to 2x squared times h. Now, one problem is that we've got too many variables. We've got 1 variable, 2 variables, 3 variables. And over here, we really need to have just 1 variable. When you're in third semester of calculus, you can work with more than that, but for now, you're supposed to just have 1 variable. So somehow we need to replace this h with something. And then that's going to come from this. It says that the total volume is 12 cubic meters. So as I did, I think it was on the first problem, this, I'm just going to leave it there, and I'm going to leave some space so I can do the calculus right here. And then somewhere else on the paper, I'm going to do the algebra over here. Volume is equal to 2x squared times h. That's the formula I got from this picture. And in this problem, it says volume is 12. And then over here on the algebra side, we could solve for h. It's going to be 12, and then divide both sides by 2x squared. And then reduce, it's going to say that h is equal to 6 over x squared. So now we know what h is equal to. We can take that and substitute in for h over here. So let me slide over. So our new function is volume equals 2x squared times, replace h with 6 over x squared. And then that seems strange to me because then the x squares are going to cancel. This seems strange because then it would just leave you the number 12. And I know in calculus you're supposed to take the derivative, and if this is just the number 12, the derivative is 0, and then we could never solve for x. So that means I'm missing something. Oh, I know, I never read the rest of the question. Sorry. What width? So in other words, solve for x. So this says solve for x. To use the least amount of material. Oh, so material is not volume. So this part, although my algebra was correct, that's not what I'm supposed to be doing. What I'm supposed to do is find out about the amount of material. So in other words, I need to know if this is made of cardboard, how much cardboard is right here on the front. So that would be x by h. So the main thing is asking about what's called surface area. So if it was made out of cardboard, how much cardboard or how much surface area is needed. So this algebra over here and this over here, that can just stay there for now. But my main equation is going to be about the surface area or the amount of material. So I'll call it S for surface area, and it's usually called a capital S because the lowercase s is used for distance, capital S for surface area. So that's going to be, like I said, this front side right here. Don't be jealous of my 3D drawing. With enough work, you can do it too. Like I said, that's going to be x by h. But there's going to be a front and a back. So that means I've got x by h in the front and x by h in the back. So there's two of those. Plus, there's going to be the right side, which is going to be 2x by h. And there's going to be the right side and the left side. So there's two of those. And then this one said it has an open top. Right here it says an open top. So we don't need to count the top, but we do need to count the bottom. And the bottom is going to be x by 2x. And let's see if we can combine terms. This has xh and this has xh. So this is 2xh's and this is 4 of them. There's 6xh's. And then this is going to be 2x squared. All right, now when I did this and I said, hey, let's replace this h, what happened is I got something that was only a number, didn't have variables. And then my brain said, that's weird. Where's the variable x? It canceled, so that can't be right. Scratch that out. But notice that we can do the same thing over here, replace h. So recall from over here, h is 6 over x squared, so substitute that right here. And then let me just simplify. This would be 36. One of these x's would cancel, but it would still leave one in the denominator. So it's 36 over x. And then we're supposed to find out the least amount of material. So this part right here is telling you set the derivative equal to 0 and find the minimum. So just like we did on that previous problem right here, this was the minimum when x equals 1 and the derivative equals 0 there. So we're going to do the same thing. Take the derivative and set it equal to 0. So the derivative, well again, this right here, you could, for the moment, just ignore the 36. This is like 1 over x. So the derivative is negative 1 over x squared. The 36 just stays there. The derivative of this is plus 4x. So one more time, notice that x cannot equal 0. But then again, that makes sense because if x equals 0, this side would be 0, and that's not a very good box if one side has 0 meters. If it has 0 meters, that doesn't make sense. So x can't equal 0 in this problem. Next, take the derivative and set it equal to 0. And then I'm going to need to finish the algebra over here. So take this and set it equal to 0, like I've already done twice. Get rid of the fraction, multiply both sides by x squared. So it's going to say 0 equals negative 36 plus 4x cubed. So just distribute this x squared. You'd get negative 36 and 4x cubed. Then you could take this to the other side. It'll become positive 36. And then divide is 9. And then take cube root. And then you could use your calculator if you want a decimal to get the cube root of 9. The last thing to do is make sure that you answer the question, because all we've done is solve for x. We haven't solved for anything else. So we got this as our answer for x, and then go back and answer the question. So what width? Well, this is the width, and this is the length, and this is the height. So the question was actually only asking for the width, which is x. So we actually did it. That is the width, and it would be in meters.